All right, so I started the meeting 10 minutes early. So if you have any questions about the homework, I can go over them in good detail. So if you do have any questions, please say so, because that's why I am early today. Let me first. Sorry about that. All right, so let's get started. So the topics we're going to go over are, the first thing is the universal law of gravitation, also referred to as Newton's law of gravitation. And then we're going to talk about Kepler's laws. Kepler has 3 laws, and we're going to go over all 3 of those today. Okay? So let's first go over Newton's law of gravitation. So this law basically describes what the gravitational force is between any 2 objects in the universe. Okay, so gravity is the force that pulls any object together. Okay, gravity acts between all the objects in the universe. Gravity acts between the pencils on your desk. It acts on me, on you, your lamp, your computer, your iPad. It acts on everything. Okay, and some people think that only really large objects like the Earth and the Sun can have gravitational force. But Newton proved that this is actually not true. Every single object in the universe has its own gravitational pull. So for example, my computer has its gravitational pull. Myself, I have a gravitational pull. So the reason we don't see anything moving because of this is because we're not as massive as the Earth and the Sun, which is why the gravitational force is so small, we can't even tell. So what is the law of gravitation? The law of gravitation basically defines the force of gravity between 2 objects with this formula. Okay, you guys got to remember this formula. So let me write this down. So this is the formula that Newton thought up, which describes the force between any 2 objects in the universe, the gravitational force. So let's unpack this formula. M1 refers to the mass of one of the objects. So let's say we have a calculator that's 1/2 kilograms. So if we were to have the calculator, we would put the mass of the calculator in there as M1. And then we look at the other object we're considering. So we're considering 2 objects here. And let's just say we have object 1 and object 2. And we're looking at the gravitational force they both exert on each other. Okay? Another thing to note is that Newton's gravity has a third law pair, right? If object 1 pulls on object 2 with a gravitational force, then according to Newton's third law, object 2 pulls on object 1 with the same force. So the same force is being applied towards both objects. Okay? So M1 is the mass of one of the objects, and M2 is the mass of the other object. You don't really need to, the order really doesn't matter here. And then we have r squared. What is r? R is the distance between the center of masses of these 2 objects. So what do I mean here? So we have to find the distance between the center of masses of these 2 objects. For example, if we had really large planets that were attracting each other, we wouldn't take the distance here as r. We would take the distance between their centers of mass as r. All right? And this is being squared. So that you have to remember that part. R is squared. Okay? So now we have one last thing we need to look at in this formula, which is this big G. So we all know the small g is 9.8 meters a second squared, right? So don't confuse this one with capital G. Capital G is actually what we call the universal gravitational constant. So this is a constant. This is just a number. So what this number is, 6.67 times 10 to the negative 11. Okay? So you just have to memorize this number. So G is 6.67 times 10 to the negative 11th. Okay, so this is a constant. We will just plug this value in to find our force. Okay, so this is a really important formula which describes the gravitational force acting between two objects of mass 1 and mass 2 and the distance between them. And a way I would go ahead in memorizing this formula would be to see how the masses are in the numerator, which means that the heavier the objects, the more massive they are, the greater the gravitational force, right? That's why force is directly related to the masses. And then another way to remember the radius part is that the farther away things are from each other, the weaker the gravitational force, right? If you're farther away from the Earth, you would be under a weaker gravitational force. So that's why R is in the denominator here. All right, and for G, just memorize that constant number. So you may be asking, hey, if an apple, like in Newton's famous experiment, if we have the Earth here and the apple is falling, then that means that the same force is being applied to both of these objects. Then why does the apple fall, but the Earth doesn't go up towards the apple? Well, even though the force is the same between these two objects, the Earth accelerates a lot less because its mass is so large. That's why the apple accelerates so much more than the Earth does. Okay? So the forces might be the same, but the accelerations of the two objects will be different. All right, so even though the Earth will actually go up just a teeny tiny bit, it's so small that it's negligible compared to the acceleration of the apple. All right, so do you guys have any questions about this formula? This is basically the law of gravitation. This is defined as the force equal to G m1 m2 over r squared. This is something that you guys should remember. All right, any questions? All right, we have these problems here. Once again, if you get the answer, please chat that to me. And if you get the answer and you would like to share your solution, yeah, also let me know so I can give you a chance to do that. So if you are having a little trouble, for the first one,
Wow.
for the first problem, try to visualize an arbitrary mass on the Earth and figure out what the force is acting on that mass and relate that to what you already know about the Earth's acceleration due to gravity. So how about one more minute? If you guys are stuck and you don't really know what to do, maybe if when I go over the solution, you will have a better idea of how to do problems like these. All right, so if you're stuck, maybe once I go over the solution, it'll be a little more clearer for you. So I'm going to go over the first one now. So using the universal law of gravitation and the fact that Earth has a radius of 6,380 kilometers, find the mass of the Earth. So first of all, let's just name an arbitrary mass, maybe a ball or something, or an apple. Right? Let's label this small m. So some kind of gravitational force is going to pull it down. And we can define this gravitational force using the universal law of gravitation, right? G times whatever this mass is, times the mass of the Earth. I'll label that me, over the distance r squared. So what is r in this case? Remember that r is comparing the distances between two objects' center of mass, okay? So what that means is that we don't take the distance from between the surface of the Earth for that object. We take the distance between that object and the center of the Earth. So in this case, since it's so close to the surface, we'll just call it the radius 6,380 kilometers, which alternatively is 6,380, add 3 more zeros at the end, squared meters, right? So this force is the gravitational force applying to some object with mass m. Another way you can represent this force is with the weight of the object, right? That's the same exact force. The weight of the object is the gravitational force acting on it. So weight of this object is mg. As you can see here, the masses m are going to cancel out. So at this point, we just have to move everything to this side, and then we'll have the mass of the Earth. So what's the mass of the Earth going to be? G times 6,380,000 squared divided by big G. And if you don't remember what big G is, it's 6.67 times 10 to the negative 11th. All right, so this is the mass of the Earth. So if we calculate this, we'll do 9.8 times 638,000 squared, and divide that by 6.67 times 10 to the negative 11th. So our answer is going to be So move this around. 5.98 times 10 to the 24 kilograms. All right, does everyone understand how that works? So that is quite a big number. So now for the second one, on the surface of the Earth, you experience gravitational acceleration of 9.8 meters a second, right? We all know that. And if you're on a satellite and you orbit at a distance of 6,380 kilometers above the Earth's surface, what is the gravitational acceleration acting on you? Well, as we know, the farther away you are from the center of the Earth, the lesser the gravitational acceleration is going to be, right? Because the force is directly proportional to the acceleration, F equals ma. So how do we solve this problem? Well, there's one way we can solve it. We can solve it through the universal law of gravitation. We can directly plug in values in there, just like we did for the first problem. But that's not that efficient, is it? If we notice how this satellite is orbiting at the exact radius of the Earth above the surface. So we have the radius of the Earth. The satellite is orbiting exactly that radius above the Earth. It's 2 times as far away as if it was on the surface. So 2 times as far away. So what this means is the r squared in the universal law of gravitation. This r is 2 times as big now, right? So if r is 2 times as big, then the force is 1/4 of the force on the surface, right? Because does everyone understand? So if r is 2 times as much, then r squared will make it 4 times. And since it's inversely related, the force will be 1/4 of the force on the surface. And since force is directly related to acceleration, the acceleration is also going to be 1/4 of what it is on the surface. So the acceleration is just 1/4 of 9.8. So we can just do 9.8 over 4, 2.45 meters a second squared. Okay, so in some cases, we don't need to use exactly what the universal law of gravitation is. We can just look for the proportions between the values in that formula. Okay, any questions? All right. Here's some more problems. So since you've already done that last problem, the second problem from the last slide, this problem is actually almost exactly the same as that one. All right, so I think that you should be able to work that one out as well. So again, if you get the answer, please chat that to me. And if you want to present your solution, then let me know as well. Another thing you should know for these problems is that the radius of the Earth is 6,380 kilometers. For the first problem, there are actually two parts to the problem. The first part is to calculate the acceleration of gravity on the International Space Station, and the second part is why do the astronauts feel weightless? So I'll give you guys 2 more minutes for these problems. All right, so I'm going to go over these problems now. For the first one, we want to calculate the acceleration of gravity on astronauts in the ISS if the astronauts orbit 400 kilometers above the Earth's surface. So this is just like the last problem where we want to see how many times farther these astronauts are from the center of the Earth than if they were on the surface. So if they were on the surface, they would be 6,380 kilometers away from the center. So if they're orbiting 400 kilometers above the surface, then they're at 6,780 kilometers. All right, so how many times farther away are there? So to calculate how many times farther away they are, we just need to do 6,780 divided by 6,380. 6,380. So it's around 1.06. So that's how many times farther away they are. So as we know from the universal law of gravitation, the force of gravity is inversely related to the square of the distance, right? So if we square this distance and put 1 over that, then we'll find how many times weaker the gravity will be. So let's square the value we have here, 1.13, and we take 1 over that, as seen here, and we can calculate that the gravitational force on the International Space Station is 88.5% of that on the surface. So what is this? 88.5% of 9.8 is 8.7 meters a second squared. So contrary to what many people think, the acceleration to the gravity in the ISS is actually almost as much as it is on the surface. It's actually not that much less. It's almost 90% of that on the surface. So why do astronauts feel weightless? If there's such a high amount of gravity pulling them downward, then why don't they just fall to the floor of the space station? So in reality, the space station is going around the Earth at a really high speed, right? So since it's going around at such a high speed, then the gravity, instead of making the station fall to the Earth, the gravity is influencing it to go around in centripetal acceleration. So gravity will be centripetal force, which is why the astronauts don't fall. because they're going at such a high speed around the Earth. So if you go at high enough speed, then you're not going to fall down to the Earth. All right. So now for the second question, we just need to apply the universal gravitation, law of gravitation. So this is just G times M1, M2 over R squared. Plugging these values in, we'll have 6.67 times 10 to the negative 11. Doesn't look right. Times 60 times 50 over 1 squared. Calculating this, let's do 6.67 times 10 to the negative 11 times 60 times 50. 2 times 10 to the negative 7 newtons. All right. So that is a really, really small force. So this explains why we don't feel any gravitational force between ourselves and the objects we have around us, because the force is so small, we can't detect it. And there are actually experiments people do with bowling balls that it actually shows that even small objects can have gravity. And it's really cool. Maybe I can link one of those videos in the email later. Okay, so if you want to check that out, I'll send a link to a video. So for this one, I don't think we have time for you guys to do it. So I'll explain this one right now. So the question asks for, so given the satellite orbiting at a distance r away from the center, if the Earth has mass m, then it asks for the formula for the period of the satellite's orbit. So how much time will it take for the satellite to go around the Earth one time? First of all, what is period? Kind of a review from last time. It's the distance it takes, the distance the object has to travel, which is 2 pi r, over the velocity. All right, so how can we find velocity from here? Right, the only unknown we have in this formula for period is its velocity. So how do we find velocity? Well, just like with the International Space Station, this object is going around, the satellite goes around the Earth at a very, very high speed. Okay? What does that mean? Gravity is, the force of gravity applies centripetal acceleration to the object, which means mv squared over r. Let's label this ms for m, mass of satellite. This is the centripetal force. This is equal to the gravitational force, which would be g times satellite times mass of Earth over r squared. All right, so let's do some simplifying. We've got mass of satellite on both sides. We have r here. So v squared equals g mass of Earth over r. V equals the square root of gm over r. All right, so this basically says that if a satellite is orbiting around the Earth at a distance r, then the velocity this object has to travel at to remain in the orbit is the square root of gm over r, where mass refers to the mass of the Earth. Okay, so this formula is actually something that you're going to need to use a lot. Okay, so I would highly recommend you guys to write this formula down because you're going to see this one a lot. So this is the formula for the velocity of an object in an orbit according to the mass of what it's orbiting. In this case, it will be the Earth over the radius of its orbit. All right. So given this, we can just plug this into our formula for period, 2 pi r over the square root of gm over r. Let's do some simplifying here. Oops. So basically, square root r goes up on top, gm goes on bottom. R times the square root of r is the square root of r cubed. And this is going to all go over gm. So this is the formula for period. Period equals 2 pi, the square root of r cubed over gm. So you don't actually need to memorize this one, but I do highly recommend you guys to write down the formula for the velocity of this object. All right. So now we've got Kepler's laws. So I think you guys might have heard of Kepler before. When NASA is looking for exoplanets out, which means planets outside of the solar system, they often name these planets like Kepler 103b, Kepler 103a, stuff like that. So this guy is pretty famous for what he's done with space, and we're going to go over his 3 laws, just like Newton's 3 laws today. So let's first look at the first law. What is Kepler's first law? Well, the first law states that when a planet orbits around a star, like our sun, its orbit is not perfectly circular. It's not going to be a perfect circle. It's going to be an ellipse or an oval, right? It's going to be kind of egg-shaped, all right? So that's the first law. First law says that the orbit of a planet is elliptical. It is not a perfect circle. And as a matter of fact, the star is located on one of the foci of this ellipse. So if you don't know what the focus of an ellipse is, let me give a little lesson about what an ellipse is. So what an ellipse is essentially there are 2 foci in an ellipse. And the ellipse is defined such that for any point on the ellipse, the sum of the distances to the 2 foci is going to remain constant. All right, so if we're to add the distances from any point on the ellipse to one of the 2 foci, the ellipse, that would be defining the shape of the ellipse. All right, so there are 2 foci in an ellipse. And Kepler's first law not only says that the orbit of a planet is in an ellipse, but it also says that the star is at one of the foci of the ellipse. All right, so that is the first law. What about the second law? So all these laws are going to be concerning planets going around stars, okay? So what is the second law? The second law basically says that when a planet is close to its star, since the orbit is elliptical, sometimes the planet's going to be farther away from the star, and sometimes it's going to be closer. So it basically says that if we have a small r here, the planet's going to be going at a high velocity. If the distance away from the sun is larger, then the velocity of the object will be slower. All right. So the closer the planet is to the sun, the faster it's going to be going. If it's farther away, then it's going to be going slower. And an equation we can use to define this is V1 R1 equals V2 R2. All right. So in this case, R1 is smaller than R2. So this is smaller. Let me draw my R's a little better. Since R1 is smaller than R2, then V1 has to be bigger than V2 to compensate for that, because this is an equation. All right, so this is Kepler's second law. I recommend you guys to copy this formula down. So basically, if you know about comets, orbit in very extreme ellipses. All right, so at the farthest away, the comet is going really slow, and the closer it gets to the sun, it goes really fast around this point, and then it goes slower again. Okay, so this is a real-world example of Kepler's second law. So you may be asking, hey, the universal law of gravitation says that the gravitational force is Gm1 m2 over r squared. If we look at r in this case, the planet's radius, the distance from the sun, is changing, right? It's getting smaller, it's getting bigger. It's not the same value. So what value do I use as r? Well, in most cases, the orbit of the planet is actually almost perfectly circular. It's very close to being a circle. Okay, so this is kind of an exaggerated drawing here. So most of the time, the planet's orbit is going to be almost circular, so we can neglect the difference. But for comets, for example, where the distances really, really change, then the r we use for the gravitational formula for all that, we basically take the long diagonal, essentially, of this ellipse, which is called the major axis, and we take half of this. So if this semi-major axis is called S, then S over 2 is basically the R we're going to use for this comet's gravitational force. All right. So are there any questions about that? So now let's go on to Kepler's third law. Kepler's third law. Well, from the question we just did, the question that I just solved, we got the period of an object's orbit is equal to 2 pi r cubed over gm. Right? If we square both sides to get rid of the square root, we get t squared equals 4 pi squared r cubed over gm. If we move r cubed to the other side, we get t squared over r cubed equals 4 pi squared over gm. And as you can see here, 4 pi squared, that's a constant. G is a constant. And the mass of what the object is orbiting, that's constant as well. So Kepler's third law is basically the period of an object's orbit squared over its radius cubed is constant for any object orbiting this mass. So for example, if we had the sun here, and we would have Mercury, Venus, Earth, Mars, the period of Earth's orbit squared over the radius of Earth's orbit cubed is the same thing as Mars's period squared over Mars's radius cubed, because this value is going to stay constant. 4 pi squared is constant, G is constant, the mass of the sun is constant. So that's Kepler's third law. T squared r cubed for any sort of objects orbiting the same sun, for example. For any object, if it were this far away, or if it were this far away, the period squared over its radius cubed is a constant. And this constant is defined right here, 4 pi squared over gm. Okay, so another way to write this is if we have planet 1, t1 squared over r1 squared, r1 cubed, is t2 squared over r2 cubed. And if we rewrite this, we get t1 over t2 squared equals r1 over r2 cubed. Okay, so this is Kepler's third law. The period of an object orbit is proportional to its radius cubed. Okay, so any questions about this? So you don't actually need to memorize any of this stuff. The most critical part you need to memorize is that t1 over t2 squared is the same thing as r1 over r2 cubed. Alrighty. So those are Kepler's 3 laws. So we're going to use these laws now in the questions. So once you solve the first problem here, then you can use the information you got from this problem, the answer, to solve the next problem. So use the answer from problem 1 to solve problem 2. And once again, when you get the answer, please chat that to me. Let me actually give you guys a hint here. For this one, you use Kepler's third law. All right, how about 2 more minutes? All right, I'm going to go through these problems now. So for the first one, we're given our the time it takes Mars to orbit the sun, which is basically the period of its orbit. And then we're given the Earth's radius of orbit. So using Kepler's third law, T1 over T2 squared is equal to R1 over R2 cubed. If we replace T1 and R1 as maybe T of Mars, R of Mars, and then T2 R2 is T of Earth, R of Earth. All right, so we're given two of the values here. We're given Mars's period and Earth's radius. But we also know that it takes the Earth 365 days to orbit the sun, so that's the period of Earth's orbit. So this breaks down into 687 days over 365 days. So we don't need to convert this to seconds because this is days over days. The ratio will always stay the same. All right, and finally, we just have the radius of Earth, which is 1.5 times 10 to the 11th. So now we just need to solve for the radius of Mars. So we basically have 687 over 365 squared cube root times 1.5 times 10 to the 11th. Okay, so let's simplify this. 687 over 365 squared to the 1/3 power times 1.5 times 10 to the 11th. What do we get? 2.3 times 10 to the 11th meters. All right. So any questions about that? So now we know the radius of Mars's orbit. So now let's look on to the second part of this problem. So a few years now, Elon Musk will launch people to Mars. I hope you guys are looking forward to that. And if the people on Mars want to talk to people on Earth, they use a radio to transmit messages. If the speed of radio waves is 3 times 10 to the 8th meters a second, calculate the amount of time it takes a message from Mars to be relayed to Earth if first, Mars and Earth are at the closest point to each other, and second, when they're farthest away from each other. So let's first look at when Mars and Earth are closest to each other. So let's say this is the Sun, and this is the Earth's orbit, and this is the Mars's orbit. When they're closest to each other, they're exactly aligned like this. So this is basically radius of Earth, no, actually radius of Mars minus the radius of Earth. So that will get the shortest distance they're from each other. So using this answer with this part, we're going to get 2.3 minus 1.5, and then we're going to multiply that by 10 to the 11th. So what is this? 8 times 10 to the 10th. All right. So now time equals distance over velocity. So basically the amount of time it takes for this radio message to get from Mars to Earth when they're closest together is 8 times 8 to the 10th, 8 times 10 to the 10th over 3 times 10 to the 8th. Let's to do that right now. That's going to be 4 point. My calculator is doing something weird. This is going to be 267 seconds. If we divide this by 60, this is about 4.4 minutes. All right, so that's actually quite a long time. When we call on Earth, if I were to call to China, for example, it would be almost instantaneous. But if we were to talk to Mars, it actually takes quite a long time. And it gets even longer when the radius of Mars, when they're farthest away from each other, right? Because if they're farthest away from each other, which is part B, Earth would be here and Mars would be there. So this is the radius of Earth plus the radius of Mars's orbit. So we add these together to get 2.3 plus 1.5. Try to reduce the chance of making mistakes here. So that's 3.8 times 10 to the 11th meters. So again, we'll plug this into this equation. And we solve for time. Over 3 over 10 to the 8th. So that's 1,267 seconds. If we divide that by 60 again, 21 minutes. So when Earth and Mars are far away from each other, if you were on Mars and you would want to call your friend on Earth, it would take 21 minutes for your message to get to Earth. All right. So that's probably going to make telephone calls a bit hard on Mars. So any questions about this? So the second part of this problem was more like a review of the kinematics equations. Now we have this problem here about a comet. So once you get your answer, please chat that to me. And if you want to explain your solution, let me know as well. So if you're a bit stuck, here's a hint. Use the equation that comes with the second law, Kepler's second law. So how about one more minute? So this is just a direct application of the equation with the second law. All right, I'm going to go over this problem now. So Halley's Comet or I don't know how to pronounce it. I don't know. Halley's Comet is a famous comet that is visible from Earth every 75 years. At its farthest point, Halley's Comet is 5.3 times 10 to the 9th kilometers away from the Sun and moves at 910 meters a second. At its nearest point, then Halley's Comet will be 9 times 10 to the 7th kilometers away. So what is its velocity at the nearest point? Well, the second law equation what's given with that is v1r1 equals v2r2. Okay? So that means, let's just call v1 and r1 the farthest distance. So its velocity is going to be 910 times its distance, 5.3 times 10 to the 12th, because it's in meters. All right? As we can see here, this is kilometers. So kilometers to meters to kilometers, we just multiply by 10 to the third. This is equal to v squared, v2, v at the nearest point. Let's just label that, because that's what we're going to solve for. And at the nearest point, r2 is going to be 9 times 10 to the 7th, not times 10 to the 7th, 10 to the 10th meters away. All right. Now we just need to solve this by dividing each side by 9 times 10 to the 10th. These cancel out. So what do we get? 5.3 times 10 to the 12th over 9 over 10 to the 10th times 910. It's basically 53600. That's around that much, okay? Meters a second. All right. So that's, as you can see here, the comet moves a lot faster when it's closer to the sun than it does when it's farther away. Okay, any questions? Cool. One last problem here. So I'll give you guys 2 minutes and then I'll go over the solution. All right, so I don't really want to go too much over time. So I'm going to explain this problem now. So Earth's distance away from the sun is 1.5 times 10 to the 11th meters. Determine the mass of the sun. So this is where the formula for period comes in handy, which is 2 pi r cubed over gm. All right, but you don't need to memorize this formula, right? If you don't want to memorize all this, you don't need to. An easier way to do it is to see how period is 2 pi r over v. And if you memorize that v is going to be gm over r, then you can just plug this in. It's going to be square root gm on the bottom, and then square root r on the top. R times the square root of r is the square root of r cubed. So this relates the period of orbit to the radius of the Earth's orbit with the mass of the sun. So we know what the period is. That's 365 days times 264 out, 224 hours times 60 minutes times 60 again. So that's the period. So you want to get everything into seconds first. Times 60. So what's that? The period will be 31536,000. That's the period. So period. So let's first simplify this so that we have the mass of the sun in terms of everything else. So let's first move this to the other side. T square root gm equals 2 pi square root of r cubed. Let's square everything. T squared gm equals 4 pi squared r cubed. So the mass of the sun will be 4 pi squared r cubed over t squared times g. All right, so let's do 4 times pi times r cubed. R is given here. 1.5. Let me first do that. 1.5 times 10 to the 11th cubed times 4 times pi squared over the period of orbit, which we found here, squared. So 31536,000. And divide that by g, which is 6.67 times 10 to the negative 11th. The mass of the sun is 2 times 10 to the 30th kilograms. All right. So this is a problem where it shows that memorizing this formula for velocity, it comes in handy a lot. Okay. And so the sun's mass is 2 times 10 to the 30th kilograms, and that is huge. Okay. So we don't actually need to put the sun on a scale, essentially, and this is how we can find out what the sun's mass is without actually weighing it. All right. So I think that's pretty cool. So that will be the end of class today. So I hope you guys enjoyed, and I'll see you guys next time. If you want to see a demo of how small objects have gravitational pull on each other, I'll send you guys a video of that through the email. All right. So I'll see you guys later. Bye.